temperature changes were not that difficult for us because everybody works with those on a daily basis. There's not a day goes by you don't put water in the freezer or the refrigerator or something in the refrigerator, and not a day goes by that you don't heat something up on a stove. Okay, so we're used to dealing with heat, changing the phase of something all the time. What we're not used to, no one has that vacuum pump that's over there that we made the marshmallows get big in. Remember those? All right, no one has one of those around. Okay, you might have a pressure cooker at home, but you probably don't use it very often. Okay, so that's what I need to talk about now. And here's where our knowledge of LeChatelier's principle is really going to come into play. Because if I just say, you're going to heat up ice, everybody knows the answer. It's going to favor melting. No one's going to get that part of it wrong, even if you can't explain it. But if I say, I decrease the volume of a container, which way is favored? You have no idea. You have absolutely no idea. If I increase the pressure, which way is favored? No idea. Clueless. It's not like talking about putting water in a freezer and freezing it. So I've got my little syringe here. I'm going to talk about this way. Okay? I'm going to need you to draw 3 pictures again. Changing the volume, either pressing down on it or pulling it up. Okay? I'll show you what we're going to draw. All right? And we're going to start with this equation right here. God bless you. All right. Remember, there's not a lot of notes here. It's more about the example at this point because we've already noted notes. I'm going to answer it all first, talking about it in terms of the equation, and we'll draw our pictures underneath. Okay? What would happen if I increase the volume, that is, decrease the pressure of this container? Well, I changed my mind. I'm going to make the pictures along with it. I'm going to have you just skip a line to answer the question. I'm going to make the pictures. I want you to draw these pictures for me. We're going to draw the same guy I've got right here as a syringe. And here's how I want you to draw him 3 times again. The first picture would look like, they might leave yourself like 2 lines blank underneath this guy. All right, I don't know how big you're writing. Right, hold on. Here's my syringe before. Now, before you draw it, I want you to realize what I want you to draw. I'm going to draw one here. I'm going to draw one here. And I'm going to draw one here. It's going to be with the syringe pulled back. And I'm going to draw one over here. Same place as that one. Now, you have water in each of them. Okay. And this is going from here to here. Like that. So here, let's look at my syringe in real life too. Here he is. And all I'm doing is I'm pulling back on that syringe. I'm pulling up on it. Okay, and I'm going to leave it up there, this new place. My question to you is, what am I favoring? Evaporation or condensation? Okay, if it was down here, and I pull back up to here. Okay, let's see if we can figure this out. All right, because I have a little demo for you tomorrow. I'm going to show you on this. It's kind of interesting. It's going to illustrate this as well. Okay. All right, let's take a look. The way I'm going to illustrate this right now is by looking at these pictures. Again, I want you to draw about 10 dots. I know you don't have a lot of room here, but that's on purpose. It was 10 dots. I just missed one there. All right, 10 dots. That's 10 vapor molecules. And this guy sitting here, he's evaporating. We use red for him, evaporation, and he's condensing. I'll use blue, and they're at the same rate. He is sitting there, hanging out, all happy. You don't have to use different colors, but they're at the same rate. What happens when I pull back? Let's take a look. How many dots in the initial effect? I still have only 10 dots, but it's in a bigger space. What happened to the concentration of the vapor molecules? Still only 10 dots right now. What happened to the concentration of the vapor molecules? It went down. I basically was removing vapor, wasn't I? Right? So what's happened here? What do you think is going to be favored? Well, it's not necessarily that the evaporation, if the temperature is the same, the evaporation is going to be basically the same length of arrow. But what's going to be smaller? The rate of condensation. There's fewer of those guys able to bang into the surface. So that arrow will be smaller. See that? Now, you would not have predicted that. And there's something very neat you're going to see tomorrow. I don't want to spoil the surprise. In that vacuum chamber that I'm going to do. All right, tomorrow is another demo. Did enough of them today. Plus, I want to do it on the same day because hooking that thing up is a pain in the neck. And the other class, I didn't get to it today. All right, so that pretty much answers your question. I'm asking you who's favored when you do this. What is the answer to that? Who's favored? Evaporation is favored, correct? All right. Let's write that down as my answer. I'm going to come back. I'm going to finish that last one up in a second. But, yeah, it favors a forward direction because it's going to try to replace that missing vapor, the one that you pull back on that plunger. When you pull back on that plunger, you were making the space bigger and not as many vapor molecules per unit volume. But the thing is, let's say I made the size of the container. I meant to make it about twice as big. It looks like I made it more like about 3 times as big. But let's say I made it about twice as big. Eventually, since they're evaporating faster than they're condensing, I'm going to get more than just 10, aren't I? And eventually, it will be to the same concentration it was before. At that point, your rates of evaporation and condensation will be equal again, because although the rate of evaporation never really changed, the rate of condensation as it went from here to here kept creeping up and up and up and up and up until eventually they reestablished equilibrium at where they were. So I hope you all, by the way, the actual description of what's going on between each of these is obviously, in this case, you are increasing the volume or decreasing the pressure. Either one. Decreasing the pressure or increasing the volume. Which, by the way, that's why I lumped these two guys together. I don't think I made that clear to begin with. Pressure and volume, as you already know, are related how? Inversely, right, from Boyle's law. Good. All right. Now, this will help answer the last question you'll need, I hope, for the, I have to finish it too. I'm not going to have you draw another one of these. Because when I do it the other way, guys, what am I going to, don't do this. When I give you the answer for increasing the pressure, it's just going that way, isn't it, right? You just reverse everything. Okay, so I'm not going to have you draw it again. Let's just get the notes for it and then talk about our last answer for a scenario kind of question. Increasing the pressure is, of course, going exactly the opposite. You're pushing down on that plunger. He was up here, and now I'm pushing down. I got less space. Less space, same number of molecules. It's going to definitely be condensing more than evaporating. All right, I'm going to favor reverse. Because basically what I did is I made the concentration of that vapor higher by doing that. In a smaller space, the concentration is greater. It's going to favor evaporation. I'm sorry, going to favor condensation over evaporation. And that's your answer to that guy. It's the opposite. Oops, sorry. All right, time for the last scenario kind of question. I talked about why sweating cools you off. I talked to you about popcorn, why it burns you. Let me talk to you now about the last question I might ask you about. Well, it's actually not the last. There's still some more I'm going to talk about. What is it about sweating on a humid day? What's the deal with that? Let's take a look at the possibility. You don't need to draw these. I just want to show you, okay? All right. Now remember, on a humid day, it's not a closed container, but if I were to draw 2 beakers with water on it, right? Say this is your hand, and there's water on top of here, and there's water in here, and both days it's 90 degrees. That's pretty hot. So the evaporation on both days is basically the same, right? But here's a dry day. On a dry day, very few water molecules above your skin, right? Not a lot of water in the air. On a humid day, lots of water molecules above your skin, right? So what's happening on the dry day? Well, you're getting some condensation, I'm sure, very little, because there's just not many water molecules above the bang into the surface of your skin. But you're getting a lot more condensation. Your net rate of evaporation on a humid day, your net rate of loss of water, is less. And that's a big deal, because you're just not taking as much energy with you as you go, right? As it evaporates. It's just not evaporating off your skin as fast. A lot of people say, oh, I sweat more. I sweat more on a humid day. In reality, the sweat just lays on your skin longer in a humid day. It doesn't evaporate as much on a humid day. You see what I'm saying? And because of that, you don't get cooled off. Actually, we're used to living in the Northeast, and we get pretty humid weather most of the time in the summer. You don't get a whole lot of beautiful dry days like they get out west. But out west, they get mostly dry days. Here, if you're exercising outside on a really hot and humid day, you run the risk of heat stroke very simply because your body can't cool itself off. It's just not evaporating enough water off of it to take enough energy with it. Out west, you do the same exercise, same heat, you'd be more of a case of running dehydration, because you would be feeling okay for most of the time. Why? Because the sweat you put on your skin is evaporating off, and it's cooling your body enough. But what are you losing? Water. Tons and tons of water. You'll feel it worse here, probably on a hot, humid day. I mean, everybody does. You know that. You start working outside, you feel worse on a hot, humid day than you feel on a dry day. You get to cool yourself off a little bit better. But there's two different kinds of risk. You can run the risk of dehydration versus on a dry day where you're evaporating a lot, you feel okay until you don't feel okay. And then, but on a humid day, you can't cool yourself off. You get dizzy, lightheaded. There's a lot of a lot of problems with that with exercise. So basically, that's the reason why. If I ask you, why don't you cool yourself off as well on a humid day? Very simple. The water simply is not evaporating off as much, and therefore it's not taking energy with it, and therefore it doesn't cool you down very much. You see? One last thing I could show you, too, using the same analogy. Anybody have a pressure cooker at home? Anybody ever cook with a pressure cooker? Parents ever do? Well, let's ask you this. Anybody do any canning? Any of your parents do canning? Do they still use pressure cookers? Some probably not. Most of the time, people don't do it anymore. They used to boil the cans or whatever. But in the old days, they used to use pressure cookers a lot to cook and to can. And the reason for a pressure cooker is very simple. A pressure cooker increases the pressure. Okay? If I'm increasing the pressure on something, okay, I'm favoring the reverse direction. Now, this will be a little bit easier to explain once we learn about vapor pressure. But the fact is, it makes it harder for it to evaporate. So I can actually have to heat that temperature up higher. I have to heat them up more to get it to the boiling point. So when I'm cooking in a pressure cooker, what am I cooking? If I put my spaghetti in water, all right, I put my spaghetti in water on the stove. What's the temperature of the boiling water? 212 Fahrenheit or 100 degrees Celsius. But if I put it in water that's boiling in a pressure cooker, the temperature is higher than that. It's higher than 100 degrees because the pressure made it harder for it to overcome that boiling. This will make more sense to you tomorrow when I do my other little demo I want to show you. Okay, and I'll come back to this one again, but I just kind of hit the head to that right now. All right? Now, I don't have